Researchers working with the James Webb Space Telescope have reported perhaps the most compelling signs to date of life beyond our solar system. According to their data, chemical substances have been detected in the atmosphere of exoplanet K218b that, on Earth, are produced only by living organisms. We're talking about a gas called dimethyl sulfide, or DMS, which in Earth's conditions is mainly released by microscopic marine algae known as phytoplankton. Researchers suggest this could point to microbial life existing on this planet. However, it's too soon to claim we found alien civilizations. This is just a possible biosignature, signs of biological activity, which is still an incredible breakthrough either way. To draw firm conclusions, more observations are needed, yet this finding might be a game changer, bringing us closer to answering one of humanity's oldest and most profound questions. Are we alone in the universe? One thing's for sure. Today we know more about K218b than ever before. Its atmosphere, the conditions around it, the influence of its nearby star, and even the surface of this remarkable planet. And right here on Space Unraveled, we're diving into all of this, plus a bit about aliens. Let's get started. The James Webb Space Telescope, the most powerful of its kind right now, has been gathering data on the fascinating exoplanet K218b. This planet is roughly twice the size of Earth and sits in a system 120 light-years away from us in the constellation Leo. What's grabbing astronomers' attention is that its atmosphere contains chemical compounds that, on Earth, are made solely by living things, specifically dimethyl sulfide, or DMS, produced mostly by phytoplankton in ocean environments. So finding these organic traces in the atmosphere of a far-off planet has sparked huge excitement and led to the idea that K218b might not only have marine life, but could be entirely covered by an ocean, one that, thanks to its nearby star, might generate massive tsunamis. But before we dig into those intriguing details, let's first explore how ocean planets in distant systems come to be. Ocean planets are a special type made up mostly of ice, rocky materials, and metals. Depending on how far they are from their parent star, they can be fully blanketed by a liquid water ocean up to 100 kilometers deep. The exact depth varies with the planet's radius. At greater depths, the pressure gets so intense that water can't stay liquid anymore and turns solid, forming different types of ice. If, while a planetary system is forming far from its star, a protoplanet reaches a mass of about 10 Earth masses, it gets big enough to pull in hydrogen and helium, eventually becoming a gas giant. A planet with a bit less mass, say 6 to 8 Earth masses, that doesn't hit that 10 Earth mass threshold ends up made mostly of ice and rock, like the moons of giant planets in our solar system. If this kind of planet is massive enough to secure its own orbit around the star without getting snagged by a nearby gas giant, yet not massive enough to grab hydrogen and helium from the gas dust cloud it formed in, then in a simple model, you get an icy planet, about half ice, half solid rock, making it a bitterly cold and unwelcoming place. But over time, due to strong turbulent shifts that can happen in the protoplanetary gas dust disk, changing the planet's orbit, this icy world might drift close enough to its star for its outer icy shell to melt, leaving it completely covered by a liquid water ocean between 70 and 140 kilometers deep. The pressure at the bottom of that ocean, around 15,000 atmospheres, is enough to create polymorphic ice forms, heavier than liquid water, that won't ever melt under that kind of force. Below that lies a solid crust of various ice types, about 5,000 kilometers thick, and finally a solid core with a radius of roughly 8,000 kilometers, made mostly of rocky mantle and metal. Yes, ocean planets are actually super rare. You could almost count them on one hand. And yet the James Webb Space Telescope has spotted one just like this. And here on Space Unraveled, we're thrilled to bring you these fresh details as we kick off our new channel. So this planet, K218b, orbits its star, K218, every 33 days and gets about 5% more light than Earth does from the Sun. It used to be thought that this planet was a type of gas dwarf, a mini Neptune, something midway between Earth's solid surface and gas giants like Uranus and Neptune. But new research hints that K218b might actually be a Haitian planet. High-shin planets are ones fully covered in water, and they're thought to hold moderate temperatures and conditions that could support life on their surfaces. The exact makeup of its atmosphere is still being figured out, but we know it's got hydrogen, helium, carbon dioxide, and methane. Kind of like Earth's early days. That's why this exoplanet absolutely earns the title of a water world. What's most exciting is the possible detection of dimethyl sulfide traces. They haven't confirmed this organic compound outright, just signs it might be there, but that alone is a pretty cool find. On Earth, this stuff comes only from bacteria, water-floating plankton, and some algae, usually bacteria in wastewater or sewage, which partly explains that bad smell we notice. But in tiny amounts, it gives sea air that crisp, refreshing scent. But don't start planning to colonize it just yet. Stick around, and let's build this Space Unraveled community together by hitting subscribe and sharing your thoughts in the comments. The system this ocean planet's in has a star unlike our sun. It's a red dwarf, dimmer and cooler than our own star. It steadily glows and lights up its planet, giving it plenty of light and warmth, about as much as Earth gets, since it's in what's called the habitable zone. But since it's a red dwarf, things aren't totally clear-cut. Red dwarfs are the smallest, most common, and longest living stars in the galaxy. Superflares happen more with younger, wilder red dwarfs, packing power up to 1,000 times stronger than those from older stars. These outbursts dwarf anything we've ever seen on the sun, and probably affect the planet's habitability at least somewhat. These flares can definitely strip away planetary atmospheres, but that doesn't automatically mean doom for any life forms we don't yet know about. Plus, there could be processes on this exoplanet that restore its atmosphere. It's a tough place for sure, and astronomers aren't ready to call it lifeless just yet. But there's more. Those intense flare attacks might mess with the planet's ocean tides and inner workings, meaning huge water masses could suddenly turn into jaw-dropping giant waves. But how big could they get? First, let's break down how tsunamis differ from those little waves you see at the beach. The difference between these two wave types isn't just size or height. The biggest thing setting tsunamis apart from regular waves is how they start. Regular waves come from wind and rarely wreck things as badly as tsunamis do, though they can still mess up coastal stuff a bit, usually just a few meters from shore. Tsunamis, though, kick off far from the coast, usually from underwater earthquakes, volcanic eruptions, or landslides. Landslides don't often cause big tsunamis, but one did trigger the tallest in history. About 85% of tsunamis come from underwater quakes. Hard to believe, but the highest tsunami ever hit over 460 meters tall at about 160 kilometers per hour. Not back in dinosaur days, but just over 50 years ago, on July 9, 1958, in Alaska, sparked by a landslide off mountains about a kilometer high. Millions of cubic meters of rock and ice crashed into the water, unleashing a monster wave. Crazy thing is, water seems soft and safe, but a 1 meter by 1 meter cube of seawater weighs about a ton. A tsunami hauls hundreds of millions of tons of water at over 100 kilometers per hour. That kind of wave can kill on first splash, and without some sci-fi gear, survival odds are slim. That's why K218b might be a brutal world for us. Yep, for us. But it's got the right amount of carbon and not as many Earth crust minerals that dissolve in oceans to pull carbon from the air. These planets, already loaded with water, just need to keep carbon cycling between the atmosphere and ocean, which in the right balance is enough to stay stable. Early models figured you'd need stars like our own for this, but the data's looking good for red dwarf stars too. Planets in systems with even feisty red dwarfs are seen as solid bets for life, since these stars can offer a steady setup for way longer than stars like our sun. Researchers say these conditions could work for planets around red dwarfs, like K218b. In theory, all it takes is steady starlight. To nail this down, we need more detailed observations. That's what the James Webb is up to right now, using its infrared sensors for extra spectral analysis to spot other biosignatures and confirm organic stuff is there. For now, this is the only way we've got to hunt for alien life in other planetary systems. And maybe under that water lies a huge water world still out of our reach. What do you think? Could K218b host alien life? Drop your thoughts in the comments, Subscribe to Space Unraveled and hit the bell so you don't miss our next video as we build this new community together. Tell us how we can make this channel even better.